because I'm like, biology or chemistry? More math. Equals easier for me.
More math?
Yes.
What?
Yeah, well, I'm an accounting and economics double
Okay,
major,
okay.
so my entire life is just
Well, actually, no,
Your
that's
entire life is numbers.
Yes,
It
exactly.
is or it isn't. There's no grade.
Yeah.
And I was like, I
I
remember chemistry from high school with a lot of numbers, so
There's no
chemistry.
gray area in that,
No.
and I like that. There's no opinion. Great.
Well, I guess let's get started, everyone. Well, thank you for coming, and today we'll go over this problem together. We'll review for the exam. And if we have time, though I doubt it, we'll go over Chapter 7. If you want to get ahead, I please implore you to look at Chapter 7 on your own. Also, the exam is going to be Saturday. Okay, Saturday. I'll give you more information about it. But first, let's go over this problem. This problem is on Hess's Law. So in Hess's Law, basically we're asked to find the delta H of a reaction. Okay, so we're going to call this the target reaction. So this would be the target. And we need to find the delta H of this target reaction. All right. Don't forget now the definition of delta H. Okay, delta H is the change in enthalpy. Okay, final enthalpy minus initial enthalpy. And really, what we're talking about with enthalpy is heat flow. Heat, lowercase q. Heat flow. So does heat come from the reaction to the beaker, from the beaker to the universe, beaker to the room, to the state, to the universe? Does the heat dissipate like that? In that case, your delta H will have a negative sign. Or does heat, Q, lowercase q, come from the universe to the reaction? Okay, in that case, the delta H will be positive. Oh, don't worry. I'll throw these like they're money. I wish, but... Right, so delta H would be positive. If heat is coming, let's say you're my universe, I'm the system. Even the beaker, I want you to know, the beaker, the container, is also the surroundings, right? And if it takes in heat from the universe, then the delta H is going to be positive. We call this endothermic, and if it's negative, we call it exothermic. All right, so this is the reaction. And what is our delta H? Well, notice we have three reactions here, 1, 2, and 3, that we know the delta H of. So somehow in Hess's Law, we're going to have to do some sort of gymnastics. What do I mean by gymnastics? Kind of like you got to flip things around, move things around, even in some cases multiply things, multiply reactions through. So I'd like to bring your attention here when we solve this problem. First, I'd like to bring your attention to the N2 gas and the 3H2 gas. Okay, you guys see that? Okay. You guys hopefully know that it's on the product side of this equation. Okay, it's on the product side. And so let's let me bring your attention now to reaction 2. In reaction 2, the N2 and the 3H2 are also on the product side, is it not so? Okay. So I think that's good. We're going to have to try to manipulate these three equations that we know the delta H. Let me bring your attention to the CH2O gas. The CH2O gas is also on the product side, is it not so? Well, now let me bring your attention to reaction 3. Okay, housed in this box is the CH2O, but it's on the reactant side. It's on the reactant side. Okay. Target, it's on the product side, this CH2O. So the first thing, now there's many ways you can do this. First thing I would do is I would reverse reaction 3. going to flip reaction 3. When we flip reaction 3, what becomes the products now are the reactants. What becomes the reactants now becomes the products. So let's write this down flipped. CH4 liquid is going to go to CH2O gas plus H2 gas. Okay. The thing is, after you flip a reaction, the delta H also flips. Here, it flips from positive to negative. Okay? Here, it flips from positive to negative. All right, and so now I got my CH2O. Let me box this now. It's in the product side. Just like in my target, it's on the product side. What I would do now is add reaction 2 because my N2 and my 3H2 are also on the product side. So let's add reaction 2. Now remember, there's many ways to do this type of problem. Add reaction 2. Untouched, totally left alone. And that's 2NH3 gas. Goes to N2 gas plus 3H2 gas. And it's untouched, so the 57.5 remains 57.5. Because I didn't do anything to it. I didn't multiply it, I didn't flip it, I didn't do anything. All right. Now, let's look around here. You see the N2H4 liquid? That's on the reactant side of my target. So the N2H4 liquid is on the product side on reaction 1. Okay. The CH4 liquid here, it's on the reactant side of my target. And it's on the reactant side of my target too. You see here? So maybe some of you can see this. My next step here is I'm going to flip reaction 1. Okay, reverse reaction 1. Okay, why am I reversing reaction 1? Let's write it down. Reversing reaction 1, we get N2H4 liquid plus H2 gas goes to 2NH3 gas. Okay, if I reverse reaction 1, this 22.5 becomes minus 22.5, is it not? Because I flipped it. So what was once endothermic now, because I flipped it, becomes negative. It's now exothermic. And you can see here now my N2H4 in the blue circle is on the same side as my target. So there's a question like this on the quiz, because I know this because the student came to me and I helped her out on it. So something like this is also on quiz 3. All right, so doing all of this, something very nice happens if you follow my blue pen. The 2NH3 gas cancels with the 2NH3 gas. The H2 here, you guys see this? The H2 here cancels out with the H2 there. And let's write what we have. I think I canceled out everything. We have N2H4 liquid plus CH4O liquid goes to CH2O gas plus N2 gas plus 3H2 gas. So I got my target. See, that's what you want to do. You want to get your target again. And what is our delta H? That's what we want to find. our delta H, we just add all of these enthalpies up. So it's going to be minus 81.2 kilojoules plus 57.5 kilojoules plus a minus 22.5 kilojoules. Okay, so you add all these up, and you get the target, add up the enthalpies, and on my calculator I'm getting minus 46.2 kilojoules. Okay, it's still exothermic. Why do I say it's exothermic? Because delta H is negative. So that's how you do a Hess's Law problem. So if you've done the lab, some of you have already turned in your lab reports. There's a huge Hess's Law, that post lab. I don't know if you did it. That's a crazy Hess's Law problem.
It was terrible.
It was terrible. So hopefully that video I recorded helped. So something like that on the test, except you'll have 2 equations, not 3, to mess around with. All right, so let's go over this exam here. All right, so I figured we'll do the same thing as we did last time. It seemed to work. Hopefully we'll keep our fingers crossed that it also works this time. If not, you can email me and we'll do something about it, or I'll do something about it. But test 3 is going to be this Saturday, and that's the 24th. And that's this Saturday. There's a thing that's going to open up this Saturday. That's 15 multiple choice questions. All right, so it's going to be open all day. Once you log in, you have about 2 hours or 2.5 hours to do the 15 multiple choice questions. And there's a problem set that will open up on Thursday, I believe, Thursday. And that opens up Thursday. This is where you want to show your work. And this you want to upload to Canvas, obviously Saturday. The problem set, I assign it so that you can show your work, show the process, and yeah. All right, so that part 1 and part 2 multiple choice problem set is going to be your exam. And the way my system works is I always have my quizzes due the same day as the test. So quiz 3 is going to be due the 24th. Okay, it's your second to last quiz. I also dropped the lowest quiz. All right, I think Joshua brought this up, so I'll bring it to our attention about the lab situation. There's our last 2 labs start today. Okay, the lab that you're going to do with me and Larissa is solubility within a family. Okay, that's something you're going to do with us. And then the computer lab is Lewis structures or molecular models. I will not be able to lecture on this till maybe the first or second week of first or second week of November. First or second week of, why did I say Thursday? First or second week of November. So definitely if you want to get ahead, you can do that, but that's your computer lab. Just realize your lecture for this, your formal lecture for this computer lab will be a little bit later than expected. Right, so that's what we're going to do for the next 3 weeks, and then we're done with the labs, and you'll have to turn in your lab notebook for some points, 100 points. All right, let's focus on this Saturday's test. It's going to be on Chapter 5, which is on gases, and then Chapter 6, which is on energy thermodynamics. So as a problem here, let's say we have an equation, CH4 plus 2O2 gas goes to CO2 gas plus 2H2O liquid. Okay. So if you have an equation like this, first thing you want to do, like all equations, is to make sure it's balanced, correct? Make sure it's balanced. So let's say I tell you that we have 15 moles of CH4. Okay, this is a type of problem you'll get. 15 moles of CH4. And then that problem asks you what is the volume of CO2 gas that you get from this reaction, starting out with 15 moles of CH4. And I also tell you that the temperature is 23 degrees C, and then the pressure is 0.985 atmospheres. And R is a constant. I'll give you R so you do not memorize it. 0.4 liters atmospheres over mole Kelvin. So don't have to worry about R. But these are the conditions. So what's the volume of the gas that is occupied when you do this reaction and you start out with 15 moles of CH4. CH4 is called methane. All right, so the first thing you need to do is understand the equation you'll use is PV equals nRT. We want to find the volume of CO2. So that's going to be nRT over P. Okay. We have everything, but we do not have the volume. We do not have the n of number of moles of CO2. So we get the number of moles of CO2 by the fact that this is balanced. And we know that we start out with 15 moles of CH4. For every 1 mole of CH4, it's balanced, right? Balanced, balanced, balanced. So for every 1 mole of CH4, there's 1 mole of CO2. I say that because the equation is balanced. And that will give us 15 moles of CO2. So that is our N. We have everything to solve this problem. So 15 moles CO2 is N. R, something I'll give you. 0.0821 liters times atmosphere over a mole Kelvin. T, okay, this is important. What do we have to do with T anytime we do gas laws? Yep, Zach is right. Convert it to Kelvin, okay? Convert to Kelvin, and convert to Kelvin. Okay, it's super important. You convert to Kelvin. And then the pressure is 0.985 atmospheres. So looking here, cancel out your units. Moles, moles cancel. Atmosphere, atmosphere cancels. Kelvin, Kelvin cancels. So doing this in our calculator, I'm getting something around, okay, I don't have my calculator, oh yeah, I do. I think it's around 370 liters. Okay. So let me move ahead just in the interest of trying to get as much as I can. Next question is on STP. Okay, so what is STP? What are those two conditions? It's standard temperature and pressure, first of all. Standard temperature and pressure. So what's our standard temperature? Okay, 0 degrees, but never use degree C. Okay, always use Kelvin. And what is our standard pressure? 1 atm. Okay, 1 atm. And that's it. That's all with regards to STP. Okay, it's nothing more, nothing less. It just so happens, that if you have 1 mole of the ideal gas at STP, okay, it doesn't matter how big, how small, oxygen, cyanide, it doesn't matter. If you just happen to have 1 mole at STP, then the volume occupied is 22.4 liters, kind of like this STP box. That's only if you have 1 mole. But 22.4 liters and 1 mole is not STP. Okay, so STP is this and this only. Temperature 273 Kelvin, and pressure 1 atmosphere. Also, the gas laws. Okay, we have our ideal gas law, PV equals nRT. Okay, but we also have within that the sub-laws. We also have within that the sub-laws. So what are these sub-laws? If you increase the pressure, the volume goes down. Okay, increasing the pressure, volume goes down. Okay, it's kind of like here, class, let's not have me lecture in this room. Let's all go lecture. I'll lecture in the closet. Okay, definitely less volume, and you'll face a lot of pressure. Okay, our elbows will hit each other and all that stuff. So pressure, volume. Same thing with a gas. Okay, so less volume, more collisions, more pressure. This is called Boyle's law, and it's the only one that we study that's indirect. As one goes up, the other goes down. It's the only one that's indirect. The other ones are direct. As an example, if you increase the temperature of a gas, the gas actually expands. It pushes above the piston, like in your car. So if your temperature goes up, your volume goes up. This is called Charles' law, and it's direct. As one goes up, the other one also goes up. Also, as you increase the temperature, what else happens? Is there more collisions or less collisions? If I increase the temperature, the molecules are going to collide more, right? Is it not so? Yes, it is so. So increase the temperature, the pressure goes up. This is also Charles' law, and it's also direct. As one goes up, the other one goes up. Everything else being constant. As temperature goes up, pressure goes up. And then finally, blowing a balloon. Okay, inflating a basketball. That is Avogadro's law. Okay, increase the number of moles of a gas in a balloon or in a basketball, soccer ball, the volume goes up. This is Avogadro's law, and it's also direct.
What are the equations for those?
All of the equations actually come from PV equals nRT.
Okay.
I can tell you for Boyle's law, because that's what will be on the exam, it's going to be P1 V1 equals P2 V2. I can tell you the other ones. Since the other ones are direct, it's going to be V1 over T1, new temperature, new volume. Okay. Same thing with Charles' law, a direct one. P1 at a T1, change the pressure. P2 will get a new temperature T2. Okay. And volume at a certain number of moles, change the volume to V2, the number of moles becomes N2. So actually those are the equations. Okay. Out of which this is the one that you'll see on the exam, or you will employ on the exam. Alright, so this is the one that you're going to see on the exam. So let's do a practice problem with this. P1 V1 equals P2 V2. Right, I'll have these notes available in case I'm going too fast, but I want to get as much done possible. Okay. So let's say we have P1 V1 equals P2 V2. So remember, I changed the pressure, the volume changes automatically, everything else being constant. I change the pressure, I get a new volume. So let's say I have a pressure P1 of 1 atmosphere, and at this pressure I have a volume of 6 liters. So I mess up the system. How do I mess up the system? I mess it up by increasing the volume to 10 liters. Okay, I could also decrease the volume. I could do whatever to the volume. The minute I change the volume, either increase or decrease, everything else being constant, the minute I change the volume, either increase or decrease, okay, I get a new pressure, P2. So what is that new pressure, P2? You can plug it into Boyle's law. All right, so P1 is going to be 1 atmosphere. V1 is going to equal to 6 liters. P2 is something we have to solve for. And then our volume is 10 liters. Okay, so this is an example Boyle's law problem that you'll see on the test. Okay, I'll give you this Boyle's law equation, but you may want to be like Zach and know those other equations as well for your future courses. So P2 is going to be 1 atmosphere times 6 liters divided by 10 liters. Okay, be aware that the liters cancel, and that's going to be 6 divided by 10 is 3/5, which is 0.6. Okay, see, I'm good at math and numbers. It's a joke. Okay, 0.6 atmospheres. I won't take your job as an accountant, so you're better at numbers than me. 0.6 atmospheres. So that would be the answer. Okay, sometimes the question asks you to give you the answer in these units, millimeters of mercury. So if you want to do that, you're going to need this conversion factor, which you do not have to memorize. Okay? And that would be the answer in millimeters of mercury, whatever that is. That I don't know. 0.6 times 760. 456 millimeters of mercury. It's just that sometimes they give you the answer in units of millimeters of mercury, then you'll have to convert it. You do not have to memorize this conversion factor. Okay, I'll give you the conversion factors. It's not something you reference. All right, so a problem like this on the exam. Right, so your answer here is atmospheres. They give it to you in atmospheres. If you need to go to millimeters of mercury, this is the conversion factor, and I'll give you that conversion factor. All right, let's switch gears a little bit and talk about enthalpy. Okay, there's 3 different types of enthalpy. There is enthalpy at what's called the standard state. You'll see this in Chem 2, delta G naught, S naught, all the different knots. That's what this superscript means, the O superscript, and that means standard state. Okay, very specific conditions is this standard state, and those specific conditions are 1 atmosphere and 25 degrees C. All right, so that's one type of delta H, that's standard state. Another type of delta H is standard state, and you're forming 1 mole. This F stands for formation of 1 mole, and this is something you look up in the back of the book, or you look it up on the internet. Okay, formation of 1 mole. Right, so this is something you look up. This is called standard enthalpy of formation. You don't really memorize it, you just consult it. Remember, the baseline gets 0. I don't know if you remember this. The baseline elements get 0. And but anyways, you look this up in the back of the book. And then finally, there's just plain old delta H of the reaction. Okay, this is something you calculate. So 1, 2, and 3. 1 and 3 you calculate. 2 you look it up in the back. And obviously this is non-standard state, okay, because we do not have that little superscript, non-standard state. Right. Also, I mentioned this, I'll mention it again, but I'll do it a little bit quickly. If delta H of the reaction is negative, okay, you want to realize that this is called an exothermic reaction. Okay, heat Q is released. And if heat Q is released, what does that mean? It means heat is on the product side. If I release heat, it's also a product in the reaction. So heat is a product in this chemical reaction. Heat is a product. Now, if your delta H of the reaction is positive, okay, whether it's standard state or not standard state, okay, if it's positive, it's the exact opposite. We call it an endothermic reaction. Heat is required or heat is absorbed from the surroundings. Okay, if your delta H is positive, it's an endothermic reaction. Heat, lowercase q, is required or absorbed from the outside. And heat, lowercase q, is not a product, but it's required. So if it's required, it's a reactant. Right, so we have heat, which is energy that kind of gets dissipated, and then we have work. Okay, work is useful energy, like your mechanical energy, gravitational energy, whatever energy that's not heat, that energy can do work. Okay, here work is lowercase w. So remember how we did this? We have work that is done by the system. By the system. If it's done by the system, it's on you guys, my universe. It's done on the surroundings. In this particular case, the work, which is a type of energy, the work for the system will be negative. The surroundings take it, it's done on the surroundings, so it's positive. Same value, but positive in value sign, because law of conservation of energy, energy cannot be created or destroyed. Right. We can also do the opposite case. Okay, this is energy that is useful. Okay, we have work that's done by the surroundings on the system. Okay, by the surroundings on the system. That's when you guys, let's say if you're on the system and you, the universe, are the surroundings, you guys do work on me. And you do something on me so that, you know, I get revved up, okay, energetically wise. In that case, the surroundings are going to be negative in value. And the system will be positive in value. Same value, but just different sign. Again, because of the law of conservation of energy. So let's move on. Let's try to get as much as we can in there. So these are multiple choice and problem sets. Okay, both. number 6. This is a gas law problem. Okay, PV equals nRT. Okay, but I think in one of the videos, I have this derived, but you do not have to derive it on the exam. But there's actually, from the ideal gas law, there's a way to get the molecular weight. Remember, molecular weight, grams per mole? Okay, you can get the molecular weight if you know the density of the gas. I'll give you this equation, but and you can derive it. I derived it in one of the videos, but you don't have to derive anything for this test. So let's do an example problem. Okay, so let's say you are at STP. Okay, condition 1. Condition 2, we have 0.400 grams of the gas. Okay, these are all gases. And condition 3, that 0.4 grams of the gas occupies 0.280 liters. And from here, given these conditions, what is the molecular weight of this unknown gas? So yes, you can solve it utilizing this equation. Okay. So first of all, remember what density is. What is density? Mass over volume. Okay. Density, intensive property, chapter 1. Mass over volume. Okay, so that's going to go here as your density D, mass over volume. What is this R? Well, R is something I'm going to give you. It's going to be 0.0821 liters atmospheres divided by mole Kelvin. So that will be R. Okay, what is T here? Okay, what's T? 0 degrees Celsius, but we got to convert it to Kelvin, so it's going to be 273 Kelvin. Very good. Thank you, Elizabeth. And then finally, what's P? 1 atm. Okay, so we have everything that we need to plug it in and get the molecular weight. Okay, if you put in your units properly, you should see the final units of the answer. Okay, it's going to be in grams per mole. Okay, that's what molecular weight is, grams per mole. Grams per mole is the molecular weight of an element or a gas or the whatever compound. Here's a problem here on specific heat. Okay, so here's the equation that you will utilize. Q equals ms delta T. So S stands for specific heat. Okay. So it's the amount of heat in joules, specifically to raise 1 gram. For 1 gram and 1 gram only, amount of heat in joules required to raise 1 gram of anything by 1 degree C. Okay. Specific for 1 gram, amount of heat required to raise 1 gram 1 degree C. And those are the units here. Well, that is a constant, so I'll give that to you. That is a constant, so that will be given. So let's say, as an example, we have silver. We have a bar of silver. Okay, let's say we have 300 grams of silver. The element symbol for silver is Ag. And the specific heat, again, this is something, this will have to be given to you. There's no way you memorize specific heat. Let's say the specific heat is joules over grams degree C. Again, specific for 1 gram is specific heat. All right. And then we can do, what can we do with this silver, 300 grams of silver bar? We can heat it or we can cool it. Okay, we can heat it or we can cool it. So let's say we heat it. Okay, and let's say we heat it. It was originally at 10 degrees, and we increase the temperature. We get it to 75 degrees C. Okay, how much heat is required to do that? To go from 10 degrees C to 75 degrees C. So that's a type of question that you'll get. And don't forget, delta T is going to be final minus initial. Okay, final minus initial. Final temperature minus initial temperature. Final, minus initial. Final minus initial. Right. So here's a question I have to ask for you. What will be the sign of Q if you heat something? Positive or negative? Right. What happens if you cool it? Go the other direction. 75 degrees to 10 degrees C. Okay, what will be the sign for Q? It's going to be negative, right? When you cool something, where does the heat go? Where does the heat go if you heat something? It goes out to the surroundings. Okay, so yes, if it goes out to the surroundings, this silver will have a negative value for the heat. And Zach is right. If you heat something, who's heating it? Okay, the oven, you, whatever. Something from the outside is heating this 300 grams of silver. And so in that case, the Q here for the silver is going to be positive. And then final minus initial. Okay, you just plug everything in here. Final here is going to be, what is that, 75 minus 10. And then for cooling, it's going to be, final is 10 minus 75. So make sure you know what your final temperature is. Make sure you know what your initial temperature is. I do not have a problem specific to this, but you'll calculate the delta H of a reaction, probably at standard state. Okay, that little O means standard state. And you're going to utilize this equation. Some of the products, okay, minus some of the reactants. So don't forget, what does M and N mean? Okay, it's the balanced equation, the number in front of the balanced chemical equation. So this is what's called the stoichiometric coefficient, or the coefficient. Okay, so you got to make sure it's balanced. That's what M and N symbolize. And I don't have a specific example, but I'll just tell you to see homework problems. Quiz 3 and a study guide for test 3. Okay, so we did a problem, I believe, last Wednesday. Okay, also the homework chapter notes. But you're going to utilize this, and I'll give you this equation, but you got to make sure you do the math right. Okay, a lot of math errors people get. You have to distribute the minus sign, and you got to do all of that stuff. So some of the products minus some of the reactants, these individual values will be given in a table. So some of the products minus some of the reactants, some of the products minus some of the reactants. Need to balance the equation first. All right, the last 5 or so minutes. rounding things up or summarizing things up with regards to Hess's law? Let's say you have an equation here, A plus B goes to C plus D, and I tell you that delta H for this reaction is 100 kilojoules per mole. Okay, the positive sign tells you it's endothermic, right? Okay. So, what happens if I multiply, this is an example of Hess's law, and we kind of did this at the very beginning of class. Same deal here. Let's say I multiply this out by 3. Multiply this whole thing out by 3, and I have 3a plus 3b goes to 3c plus 3d. So what will be my new delta H? My new delta H will not be 100 kilojoules per mole. It's going to be 300 kilojoules per mole. Right? That's one of the rules of Hess's law. Multiply a reaction out, whether it's 3, 1, you can even do fractions, then you multiply it by that fraction, 4, 5, whatever number. Okay? And then what happens if I flip this reaction? Instead of this going one way, I flip it. 3c plus 3d goes to 3a plus 3b. Okay, what's my new delta H? Yeah, it's going to be negative 300 kilojoules per mole. Okay. So those are the only two things that you do with Hess's law. You can multiply it out, you can even multiply it by a fraction, and you can flip it, right? And here, remember the problem we did at the beginning of the class, we flip it. Flip the sign. Multiply delta H by that number. Okay. It can also be a fraction. And I think that is pretty much it. So problem sets will summarize this. Multiple choice will summarize this. And yeah, that's pretty much your exam, more or less. Any questions or comments? We have another 2 minutes or so. All right. So you guys should promise me you'll start looking at chapter 7, because I want to try to move ahead as best as I can. Right, so if I went too fast, anybody could have these notes.